Welcome to Brain Vision.
For this example, we are looking at the diffusion of glycine in water in this cylinder here. And specifically, we're looking at a case in which we have a higher concentration on the left side of our cylinder than on the right side, and that is right here. So there's going to be an overall transfer of glycine to the right, and the rate of that transfer is 4.2 times 10 to the minus 3 kilograms per second. We also have the diffusion constant and the geometry of the cylinder, the cross-sectional area and the length of the cylinder. Okay, so this problem is regarding Fick's law of diffusion, which states that the mass transferred is going to be equal to the diffusion constant times the cross-sectional area times the difference in concentrations from one side of this cylinder to the other, divided by the length of that cylinder times the time that passes, where delta C is just the difference in concentrations from the high end to the low end. So C high minus C low. All right. So what we want to figure out is, what does the concentration on the low end need to be in order for us to have this mass transfer rate here? Okay. So we're going to take our Fick's law here. We can substitute in our delta C, and then we're going to solve for the concentration on the low end. So this is dA T over L times delta C, which is CH minus CL. I'm going to multiply both sides by L over dAT so that we cancel it out on the right-hand side. So we'll have LM divided by dAT equals CH minus CL. And then we want to solve for CL, so I'll add CL to both sides. So we'll have CL plus LM over dAT is equal to CH, and then we'll subtract LM over dAT to the other side. And we would be left with that the concentration on the lower end is equal to the concentration on the higher end minus L times M over dAT. Okay. So we can see that we are actually given the mass transfer rate, not the mass and the time. So this value here is actually going to be equal to our M over T, right? Since it's a mass over time. So if we wanted to, we could substitute that out with another letter name like R or something for rate. But we can leave it as is for now and just remember that we're going to be grouping these two together as a single value. So other than that, we have our L. It's in centimeters, so we'll want to convert it to meters. And there are 100 centimeters per meter, so we're just going to move the decimal place back 2 times. Have 0.02 meters. The diffusion constant is in the proper units, and the cross-sectional area is in the correct units. Yep, meters squared per second. And it looks like our concentration on the high end is also in the correct units. So we are in a situation now where we can just calculate what our concentration on the low end is. So if we plug in all of those values, we will get that the concentration on the low end is equal to 3.02 times 10 to the minus 3 kilograms per meters cubed. So our concentration on the low end will have to be 3.02 times 10 to the minus 3 kilograms per meter cubed in order for us to have a mass transfer rate of 4.2 times 10 to the minus 3 kilograms per second, given that our high concentration is this right here.